Hello, everyone, and welcome to another Celebration of Mind session. It is with great pleasure that I will announce today's speaker. Dr. Ellie Baker has a Bachelor of Fine Arts in Sculpture from the Rhode Island School of Design and a PhD in Computer Science from Harvard University. Over the last decade, she has produced many artworks exhibited in the juried shows of mathematical art, such as the National Joint Mathematics Meeting, Bridges, and Mosaic. And she will present on the crafts, math, and the joy of turning things inside out. And without further ado, I will pass over to you, Ellie.
I will be telling a story today about how crafting projects and my design aspirations for them led me to a series of engaging puzzles and some fun mathematics that I needed to solve them. I have two co-conspirators in this work, Ellie Baker and Charles Wampler, and they're actually here with us today. I'll be giving the talk, but they're able to participate in the discussion at the end with us. So if you have questions for them at the end, that'll be great. Although my story is generally about learning some fascinating mathematics by solving crafting puzzles, the particular theme today will be about turning things inside out, or what I call inversions. And I'm going to begin right away with the project that I'm also going to end with. Oh, and also I wanted to mention that the paper that Charles and Danny and I wrote, there will be a link to it in the chat box for you. A series of puzzles and projects over multiple years led to the design of the scarf shown here, which has the very unusual and entertaining feature that it can be turned inside out to expose not just two different surfaces, but three. So it's a three-way reversible. I'll start by demonstrating it for you. And then on the way to explaining how it was made, I'll talk about the various puzzle solutions and multiple projects that led me to it over a period of years, really. As a quick aside, I want to note that I'm not trained as a mathematician. As Tiago said, I first studied art at the Rhode Island School of Design, and then later went on to study computer science, which did require learning some math, a fair amount of math, but it still left a lot of holes in my math background. But I love to craft, build, and make things, and I found that if you're a crafter, it's wise to cultivate mathematicians as friends. Just about every craft project I've ever worked on has benefited from my working with my math buddies. Here are just a few of the mathematicians that I've drawn into projects. Actually, these are the ones mostly that I've drawn into projects over the years by asking them questions about the crafting puzzles I was working on. Each of them has taught me some wonderful math along the way. So, okay, let me show you my peculiar scarf. I've got a video here of it. I'm just going to demonstrate by showing this little film strip. Okay, so the scarf has a double slotted slit in it, which you can see here in the video. It's got an orange side and a green side, and you can choose which of them to invert through. I'm going to start with the green. It has to be shaken out and straightened out after you invert it, because things get a little bit rumpled and funny, and you want to sort of shake it out and put it back in nice shape for draping on a human figure. So it does need that shaking out. So there's the green. Now the slit has changed to the original blue and side on one side and the orange. So I'm going to switch to the orange side now. And you can see this particular scarf is made out of very thin, sheer, lightweight silk. So you can even see the other fabrics running all the way through the interior, through the silk. Again, I've got to give it a good shake out to get it nicely aligned again so that it drapes well. There's the orange. It looks kind of bulky, I think, probably, but it's quite light and comfortable to wear, very comfortable. All right, now we're going to go full cycle, and you can see we're back at the original blue that I started with. There's the slit again, which is now green and orange again. So there you have it, voila. So I hope this piques your curiosity about how it was made, and we're definitely going to get to that. But first I want to trace some of the steps and puzzles along the way that led to it. So the design of this scarf had its first roots in a much earlier project, which might seem unrelated. And in some ways it is. The project was to make a beaded bracelet with a pattern of special interest to mathematicians called a 7-color Taurus map. A torus in math terminology is a donut shape. I'm not going to go into any detail about 7-color Taurus maps here because that would be a detour. And also there's a wonderful other celebration of mind talk given by Susan Goldstein on that topic. I think it's called something like Maps of Other Worlds. But anyway, here's a picture of a 7-color Taurus map. On the left here in Hydra Stone by Norton Starr, and on the right, a bead crochet bracelet that was the result of work Susan Goldstein, Sophie Summer, and I did. A decade ago, when I learned to bead crochet, I noticed that the bracelets I was making were also tori in the mathematical sense. And I wanted to make one with this 7-color Taurus map on it. For this talk, I mention it only because it was the first puzzle that inspired me also to want to make a toroidal scarf. Infinity scarves in the fashion world are also tori, and even though they may be flattened or looped or folded, they're still essentially donut-shaped surfaces. So they can exhibit this same 7-color Taurus map pattern. And sometime after making the bracelet, it occurred to me that it would be fun to make a scarf to match it. From the bracelet patterns, I already had a pretty good idea what the fabric should look like, but then there was what I assumed would be a pretty small, simple puzzle about how to sew it. So in mathematics, a torus is often represented as a square, like this, in which is made from stretchy, shrinkable, but not rippable or tearable material, with its opposite edges identified or connected. So for example, if you connect the blue top and bottom edges here, you get the cylinder shape. And then to connect the right and left edges, you're effectively connecting the cylinder ends, and that gives you the donut shape. So my cloth fabric wasn't as stretchy or shrinkable as required in this mathematical definition, but I figured I could start out with a long rectangular piece of fabric like this, which has the 7-color Taurus map on it. And still sew it together in exactly the same way. So once sewn together, it would have a longitudinal seam going around the donut hole and a meridian seam going through the donut hole. So a typical strategy in sewing is to stitch a garment inside out and then turn it later right side out to hide the raw seam edges on the interior. I figured that's how I'd sew my scarf. But the first time I tried it, I wasn't even certain that it was possible to turn a torus inside out. But I figured I'd give it a try and see what happened. So I sewed this item on the right here, inside out with the raw seam edges on the exterior. And I left a little slit in one seam, and I went to turn it inside out, hoping that I would get this object on the left, excuse me, after I did. But what happened was not what I was expecting. I'll demonstrate with another little video clip here. Okay, so here we go. We're gonna turn that inside out infinity scarf right side out. And to my amazement, it had completely changed shape. I was really, really puzzled by this. The result turned out to be a better fit for my giraffe than it was for me. So this gave rise to a new puzzle. What happened, and how can I sew my scarf to fit me instead of my giraffe? So when I went to try to understand what had happened, I did an internet search on turning a torus inside out, and that led me to this nice animation. So the good news about my project, which I discovered, is that it is possible to turn a torus inside out, but the way it works is kind of strange. If you look carefully at this animation, you'll see that the meridian rings going through the torus hole, when it gets turned inside out, swap to going around it instead. So the meridian and longitudinal rings swap roles on this inversion. But I had started out with a rectangle, not a square, because my fabric was not stretchy or shrinkable. And so it had short meridians and long longitudes. And when they swapped roles, the scarf just completely changed proportions. It was still a Taurus, but a tall, fat one instead of a long, skinny one. I knew right away that one solution to this might be to use a square piece of fabric, because then the meridians and the longitudes would be the same size. But that wouldn't give me the kind of proportions I needed for a good infinity style scarf. The solution in this case turned out to be actually pretty simple. If making it in this form and turning it out inside out gives you this form, then sew it inside out in this form and turn it right side out to get the form you wanted. It turns out seamstresses are familiar with this technique for making infinity scarves, but I discovered it on my own. So that was pretty satisfying, but here's a related puzzle which ups the ante a bit. I also had a trefoil knotted bracelet shown here, and I wanted to make a trefoil knotted scarf to match it. Can such a knotted scarf be turned inside out? And if so, what happens when you do that? And how do you sew it with hidden seams? For this scarf, the longitudinal lines are knotted. So when you turn it inside out, you get an object that looks like this X-ray vision drawing here on the upper left. It's a tall Taurus with a knotted hole. Here's the knotted hole. So if you wanted to stick your hand in through the donut hole, you'd have to have a roto-rooter arm to get through. I had to figure out how to sew it inside out in this form in order to make this scarf, or at least that was the method I used. And here are the notes I made on how to do it. Again, there should be a link in the chat box to this in case you want to try this out yourself. But it's quite a fun sort of magic trick, really. So about this time, I started noticing that there were some very fun reversible fabrics like these in fabric stores. And I began lamenting to myself how sad it was that my scarves changed shape when I inverted them. If not for that, I figured I could have made a really nice reversible infinity scarf. This puzzle is the subject of a paper that Charles Wampler and I wrote. And again, there's a link to that in the chat box as well. It was the first paper. After pondering this for a while, we discovered another geometry in addition to the square layout that will invert to the same shape. If you start with a hexagon and sew its opposite edges together, you'll also get a torus. So in other words, you sew A to A, C to C, etc., B to B. However, its geometry is not going to change shape when you invert it. Furthermore, it has some particularly nice features for an infinity scarf. You wind up with a torus with a Mobius twist, which makes it drape better on a human figure. And it folds flat into this nice little equilateral triangle with 6 layers. So you can store it neatly. And this is just one of many I made. So even though I said this scarf is made from a hexagon, this is not the only cloth layout that can be used to make it. You can preserve its geometry while moving some sections around without changing any of the connectivity to get several different layout shapes. For example, if I move this triangle here and this triangle here, I actually get an equivalent rectangular shape that can also be used to sew the scarf. In this case, I have to explicitly give it the Mobius twist when I sew it. And likewise, if we move this triangle up here, we can get a parallelogram or a rhombus shape, which forms the same scarf if you sew its opposite edges together. So there are a bunch of equivalent layouts that can be used to make the scarf. In fact, infinite, I think. In our paper, we showed that the hexagonal layout has the shortest seam length, if you're sewing it, of all possible layouts. And in fact, this turns out to be true for the very same reason that honeybees use hexagons to build their honeycombs. For sewing scarves, the different layouts each have different pros and cons, and I won't go into that now, except to mention that the parallelogram turned out to be particularly useful for the triply invertible scarf. Our first paper describes how to sew the Mobius scarf using each of these 3 layouts. So this was all great, and I happily started making a bunch of 2-way reversible scarves using this design. Here's one that I made with some fabric I got at Joann Fabrics that was reversible, but there was still a problem with it that really, really irked me. With both inversions of the scarf being used, there was no longer a good place to hide the raw seam edges on the interior. There was no interior, there were two exteriors. So I worked around this by using a sewing technique called French seams, which you can see here. And it hides the raw edges, but it leaves a visible flap on one side. So this side, it's neat, and this side over here, you can see that visible flap. So I really didn't love this because it disrupted the perfect symmetry on inversion that I was aspiring to. But initially, I didn't think there was too much I could do about it. Also around this time, I started getting bored with the limited number of reversible fabrics available in stores. I realized there was an easy solution to that. I could just stitch 2 pieces of fabric back to make my own reversibles out of a double layer. It was bulkier than commercial 1-layer reversible fabric, but if I made it with 2 very thin, lightweight fabrics, it worked pretty well. And I sewed a lot of scarves this way, including this one that was exhibited at the Joint Mathematics Meeting, Mathematical Art Show. And for it, I designed fabric that echoed the hexagonal structure of the scarf itself, and also enabled me to match the pattern perfectly at the seams so that it would feel like a really an infinite loop with no disruption. But if you look carefully, if you could zoom in on this inversion here, you'd see it still has those annoying seam flaps on one side. And deep down, I was still unhappy about that. And then one day, after having sewed many French seams, it suddenly occurred to me that because I was making my own reversible fabric out of 2 layers, unlike the single layer reversible fabric I'd found in stores, there was an empty space in between my 2 layers. And in theory, at least, I should be able to hide the seam flaps in there. Although I didn't have any idea how to access it with a sewing machine. And I remember Charles dubbed this region the inner sanctum. The question was how to get into the inner sanctum with my sewing machine. So I had a new puzzle. Was there a way to do it? If I wanted to do this on a more conventional shaped scarf like this one, sort of pillowcase shape, basically, it's easy. You just create the 2 pillowcases, you turn one of them inside out, and you stuff it inside the other one with backsides together so that they're nested. Maybe you have to tack the corners together at the end as well. And I used this approach to make this classic non-toroidal reversible scarf for Superman Clark Kent. However, what happens if you try to nest 2 toroidal scarves this way? This was a much trickier business. You can't just stuff one inside the other like you did with the pillowcases. If you try, the stuffed one's going to end up scrunched up in a ball on one side instead of looping fully around the interior in a proper nesting. So I pondered this for a while, and there is more than one solution, and some are more kludgy than others. But eventually, a particularly elegant solution came to me, which takes advantage of the strange swapping of meridians and longitudes when a torus is inverted. I'll demonstrate it for you here using a small square layout because that's simpler to implement and it makes it easier to see what's going on. But the same method can be used on the Mobius scarf layouts as well. So you start out by sewing 1 torus inside out. Then you start another torus, also inside out, but before closing the cylinder, you thread that cylinder through the hole of the first torus like this. Then when you sew the cylinder closed, you sew it so that it's linked to the other one. So they're both inside out and linked. And then you want to make sure you've left a small slit on both of them. And your next step is to just invert one. It doesn't matter which one you invert, but the one you invert will wind up on the exterior of a perfect nesting. I highly recommend that you try this experiment on your own because it's the only way to really appreciate how cool it is. If you have a couple of square cloth napkins, you can try it and check it out. Once they're nested, you can hand sew the split edges together here and here so that and of course, you're going to need to sew it in such a way that they are positioned correctly. And there's a trick to that you can read about in the paper. Once you've sewn the slit edges together, you can no longer invert just 1 torus at a time to go back to the linked state, but you can go back and forth between the 2 nested states. To review, here's a graph that summarizes all the possible states of 2 linked tori with slits. If you start out in this linked state and you invert the red one, indicated by the red arrow here, you'll end up with the red on the exterior and the blue on the interior nested. And likewise, if you invert the blue one from here, you'll end up with the blue on the exterior. If you start out in one of the nested states and you try to invert one of the interior tori, the blue one has to come along for the ride. So that's indicated by this blue dot here. And then you can go back and forth between the two nested states this way. So if you sew the slits together, the linked state is no longer possible, and the inner sanctum that Charles referred to is locked off forever. I was pretty thrilled with this new technique for making the scarves. And around this time, Danny, as a kind of a lark, suggested maybe you could make a triply invertible. And he suggested some kind of cockamamie suggestions involving multiple slits that I was pretty skeptical of. But I was intrigued by the concept, and I began thinking about it more seriously. One question that immediately came to mind was, what would happen if we nested 3 tori, one inside the other, sort of like Russian dolls are nested? It's easy to make a nesting like this. You can use the linked sewing method. Once you've got a nesting of 2, you can link a third one in and then get a triple nesting. Would this work to make a triply invertible scarf? Sadly, no. As I said, it's easy to try it out in cloth, but here also is a graphical proof that we provided in our paper, which goes through all, if you start with a triple nesting, it goes through all possible inversions and states and transitions that you could get to from that state. And for this one, the green Taurus, which is the one in the middle, in both cases, can never wind up on the exterior of a triple nesting. So there are only 2 fully nested states. Furthermore, it doesn't help if you try to add additional nestings. You'll wind up with just more links in this linked states here, but only still 2 fully triply nested states. That was a disappointment, but not to be deterred, I wondered, is there any other way to link or nest 3 tori and get a triply invertible scarf? I began thinking about this by studying this 3-link portion here, which I've repeated up here, of a graphic made by Rob Scharein, which he calls a knot zoo. It's basically a categorization of the various knots and links. He also provides an interactive 3D viewer, which I highly recommend, and there's a link to his site in the chat box. So you can look at them from different angles. So I wanted, of course, to look at the 3-ring links. So that was these up here. But I tend to want to hold things in my hand in order to understand them better. I made myself a clay model of one using Crayola Model Magic. And what you're seeing here is a picture of it. And this is the exact same link in different poses. So this is one link, but I'm showing you different photographs of it. Playing with it, I could see that it has a nice kind of symmetry in which you can pull out one link like this, and the other 2 will be positioned in a particular way. But if you swap to pulling out, say, the green one instead here, then the other 2 are also positioned in that same way, and likewise for the orange. So this is a very nice symmetry property, which was important for making a triply invertible. You want to be sure that whatever you do to one, it's going to be the same when you invert the other one. It was readily apparent to me that the first 3 links in his list here had that symmetry characteristic. I wasn't quite sure about some of the others. I think some of them actually do, but it wasn't as easy, and they just looked more complex. So these 3 seemed like a good place to start. Each one of these represents a fun puzzle in its own right. I don't know if you can figure out for each of them what will happen if you make them as cloth tori and then invert one, but I certainly couldn't visualize this in my head, although now I actually have gotten better at it. But initially, I had to make them as cloth. Here's the first one. Now, because it has this nice symmetry property I mentioned, it doesn't matter which one I invert. The other 2 will look the same after I invert one. So I'm gonna show you what happens when I invert the purple one. And I have to show it to you as an X-ray vision drawing that I did, because obviously you wouldn't be able to see through the purple fabric. And I made the slit kind of big so that I could stick my hands in there and feel around, see what was going on, and kind of peek in. And I could see that this is what the two interior tori looked like. It was nested, but it did have this kind of funny lump in it, which wasn't perfect, kind of a twist. So, okay, let's try the next one. Here's the 632 link in fabric. And when I inverted it to the purple one in this, to my amazement, I got this very strange configuration. I was really puzzled by this initially. But I noted that this ring is actually an example of a well-known link, or this link is well-known. It's called the Baromian Rings. And it has the Baromian Rings have the feature that if you remove any one ring in the link, the other two are no longer linked. So for example, if you take the blue one out here, you'll see that the red one is just laying on top of the green one. They're not actually linked. So what does this mean for our cloth version if one of them gets inverted? In fact, if you look at this X-ray vision drawing here, these two interior ones are not linked, just as we would expect with the Baromian Rings. You might have to look really carefully to convince yourself of it, but there's a neat way to convince yourself if you just take a couple of rubber bands and position them in exactly this way, just as I've done here. And I want to note that another strange thing about this is that even though they're not linked, there's no way we can sort of get them apart because they're stuck inside the outer torus. The purple one that was on the outside is holding them in this position. So it actually does work as a nesting, sort of nesting for the scarf. Continuing on, we're gonna see what happens with the third link. This one, when I inverted the 633, when I inverted the purple, I got a configuration like this in which the inner tori are simply linked. And that looks pretty promising. So it turns out that all three of these could be used, but to be useful and as a triply invertible scarf, but to be useful and pleasing as a scarf, we want to minimize any bulkiness of the interior tori. So, because we want the scarf to drape nicely and not look lumpy. And you can see here, we've got kind of a lump in it. An interesting observation is that if you could remove the outer torus, you could sort of pick up this blue ring and untwist it. And then it would look exactly like this one. So these two topologically are actually in the same configuration, but this one here is being held in this knotty shape, which was not good for a scarf. Likewise, my Baromian rings also had some knottiness in them. So on balance, comparing these three candidates, it was clear to me that the 633 did the nicest job of evenly distributing the fabric of the inner tori. So it is an excellent choice for our triply invertible, and that's the one I used. One way to understand why it works is to note that the two inner rings, the two inner tori are behaving like a single torus. Looking at the clay model here, you can sort of see that if you smush them together in your head, they're just like a single torus linked with another one. So it effectively reduces the whole thing to a simple two-way link like the one I used to make the original doubly invertible. So here's a three-way reversible version of the scarf that I made using this link structure. I designed 3 fabrics for it to illustrate the structure of the scarf itself based on those clay models I made. It's displayed in the Bridges online mathematical art exhibit this year. The fabric motifs are hand-drawn and by me and organized into this hexagonally based repeating pattern using the app iOrnament and printed with the fabric printing site Spoonflower. And I put links in the chat box to those in case people want to try those tools. They're wonderful. Of course, we're not done puzzling because the next obvious question you might have is about whether this design scales up. Could I make a quadruply invertible or a quintuply invertible or more? Looking at the clay link model in this particular configuration gave me a clue to the answer. What I wanted was to be able to add a new torus that linked through all the others while still maintaining that nice symmetry property. It turns out it's easy to do this. The added red link is symmetric to all the others in the same way. And you can keep adding just as many rings as you want in the same way. And it will still have that symmetry property where you can pull out one, which will be linked to all the others. Other people are also interested in the same link structure, even without wanting to turn anything inside out like I did. Here's a 3D print of this same 633 link that was created by Carlo Sequin. You can see in the side-by-side photos with my clay model that it is exactly the same link, but he's made it much more compact so that it looks like a single compact donut. And you can see here the single link pulled out. Carlo made a wonderful video that showing a different way of thinking about how the link scales up. And I would definitely urge you to watch his video. I've put a link to it in the chat box. Here's another one that I had made from the 3D print file he gave me, which is a 6-way link. It's a little tricky to put back together again once you take it apart, you shake it out, but here it is in a position where you can see the single link loops through all the others, and it still has the symmetry, so it doesn't matter which one you pull out, it will do that. So what this means is that the link scales up infinitely while maintaining its nice symmetry. So we have infinite scale up potential for our scarves. So in theory, I could make an infinitely invertible scarf. Haven't tried that yet. However, a 4-way invertible is certainly on my list of upcoming projects, and perhaps one of you will try some experiments with inversions as well. If you do and you learn anything interesting, please let us know. And if you're interested in learning about some other fun crafting puzzles, I have a book to plug. The 7-color Taurus bracelet that started all this turned out to be the genesis of an entire book on the topic of bead crochet pattern design. That Susan Goldstein and I wrote together. The solution to the 7-color Taurus map puzzle for bead crochet is presented in the book along with a lot of other puzzles. So please take a look at it if you're interested in bead craft at all. And that's it. And now we can take some questions and include Danny and Charles in the conversation.
So thank you so much for this beautiful presentation and these amazing designs you make. But yeah, we have a bit of time for questions.
I have a question that I could start with that I wanted to ask Danny. I don't think it ever would have occurred to me to try to figure out how to make a triply invertible scarf. I mean, I think of inversion as, there's 2 sides, that's it. But something about him or his mind led him to suggest that idea. And I'm curious how that came to him as something that could even be possible. What is it about his thinking?
Ellie, I think sometimes ignorance is bliss, as they say, and I know nothing about sewing. And maybe that gave me an edge in this process. It freed me up to think about things that, as a seamstress, you would never think about because at first glance you didn't know how to sew them. Now, I have to say, I don't really remember, but I think when I first made that suggestion, I was thinking more along the lines of the Russian dolls. And so it was you who figured out that that doesn't work and eventually figured out how to do it. But I think the answer to your question is I was ignorant enough to not filter out that idea at first glance.
Have you seen David Richter's keyring model of hop vibration? It's the same pattern as your M-linked rings.
No. If somebody could put a link to that in the chat box, I will definitely take a look at that.
Josh Holden, is there a mathematical proof of duality between links embedded in a torus and links in 3 space with one more component?
I'm going to punt that one to Charles or Danny.
The answer is I don't know if there's a mathematical proof. I kind of suspect there is. I think, it's a well-known fact that when you have 2 linked tori, well, that a torus and its exterior is equivalent to a 3-dimensional sphere. That's a known fact. And this question seems to be related to that. And I'm sure people know the answer to this. I don't know if anybody has ever written it down. I'm not at all familiar with the literature, I have to say.
Just a quick side note: people are very eager on the on the links and on all of these. So I think later on we can link to further things in the G4G YouTube channel in the description. Another question would be, to begin with trying to sewing, what fabric would you suggest? Natural or synthetic, and what weight?
Definitely want to start with lightweight fabric. The silk is really hard to work with, but it's very nice. But a lightweight synthetic the first time you try it out. Or if you don't care about it really working as a scarf, then you could use a heavier weight fabric and just to create the model. It doesn't matter if it's too bulky in that case. So something that doesn't fray too much and cut smoothly, because you've got to cut these very precise shapes out in order for it to work properly. If you don't cut the shape out right, it won't invert to the same shape.
Another question is it possible to buy these scarves anywhere? Or do you quickly need to get to learn how to sew? Yeah,
you're gonna have to learn how to make them. And I'm happy to communicate with people who are interested in this. I will tell you that making the triply invertibles is quite challenging. It should not be your first sewing project. But the doubly invertibles are not too bad to make. And I might mention that I have this one here that I made with fabric that Frank Farris designed. It's actually a 7-color, it's a kind of a 7-color Taurus where the countries are links. They're all linked together to one another. And it will eventually be, we think, available. Here it is in its triangle shape, nice triangle shape. It'll be available in some future auction for Gathering for Gardener, I believe, for sale. I don't know when. I don't know when that'll be.
Another question from the chat is if you have a knotted Taurus, a single one, and you invert it, what do you get? Which type of knot? The general knot, not necessarily the trefoil.
If you look at this picture here, the same technique that I use for the trefoil should work for I believe any general knot. I've made myself a little note to that effect here on my notes, but don't hold me to it, but I believe it's true. And I did put a link in the chat box to this document. But basically you can knot the scarf any way you like. Put it in a cylinder form, knot it any way you like, and then cuff over the edges and sew them together, which gives you, in this case, this one. But if you knotted it in some other way and then inverted it, you would get whatever that knot was.
I mean, I literally squeaked slightly when you showed the Baromian Rings model, which is one of my favorite mathematical structures.
Yeah. Isn't it cool how they end up not linked inside? It's just so weird.
Actually, it could be an idea to just have a mechanism to open and release it, so you can actually pull all three apart and put them back together somehow.
I'm hoping people will have lots of ideas and pursue this in different ways. I'm looking forward to that.
Well, it was a great pleasure. Thank you so much once more. Thank you, Daniel. Thank you, Charles, as well, for joining us and helping and discussing the mathematical questions. And thank you so much, Ellie.
Sure.
Thank you for hosting.
Thank you. Yeah, thank you for hosting. Great job.
Bye.
Bye.
Bye.